네, 한성민 씨 안녕하세요. 네, 정강목 씨 안녕하세요. 박건우 씨 안녕하세요. Okay, so it's 9 o'clock. We will start it right now. Okay, good. So, how was your homework number 4? Homework number 4. We had two different problems. So first one was solve the Laplace equation with terminal description, so contact description, and second one was the interface calculation. Interface. So without any without any predefined information about interface, you have to generate certain knowledge on interface. So usually the code give you only information about region, and there is another region. So whether they are attached or not should be decided by the developer of device simulation code, and that was your role in the last homework number 4. So how was your homework number 4? Did you have any difficulty to address these homework number 4 problems? If so, then let's have some time to discuss about your difficulties. So could you please say something about your homework? Okay, calculate interface edge. So edge here means that, so in this case edge is specified just to two vertex indexes. So v1 and v2 will a pair of these two integer numbers will completely specify an edge. So say v3 and v4. Let's say that this is your interface. Then what you have to do is provide a list of edges. So it should be v1, v2, v2, v3, and v3 and v4. That should be your answer. How about Mr. Han? So did you interpret our problem, the second problem, in this way, or you interpret it in a different way, so your result is not directly related with this answer? So could you please give me your feedback? And how about other students, Mr. Jung and Mr. Park? So did you have a okay, thank you. And did you have okay, Mr. Jung? Great. And how about Mr. Park? So mm, oh, in that sense, I should say it is better to specify edges. So your contact file is not a list of vertex nodes or vertices, but you have to do in this way. Let's just say that this is your region, and now you have a certain points which are assigned to your how can I say, context. So say this one is once again V1 and V2 and V3. Of course, V1, V2, V3 are integer numbers, arbitrary integer numbers. And when you specify this kind of structure, maybe you are prone to write down your contact file like V1, V2, V3. That seems to be quite easy. However, instead of that, as I told you in the last lecture, lecture 4, it is prepared to provide information like B1, B2, and B2, B3. Exactly same manner to specify the interface. So interface was specified as list of edges, not a collection of vertices. So now by applying this kind of description, now you understand, there is a certain edge corresponding to V1, V2, and there is another edge like V2 and V3. So if we follow the description like this, yeah, then later if we try to build the edges out of it, then we have to think about whether V1, V2 really exist. Yes, in this case, it exists. And an edge connecting V2, V3 exists. Okay, it exists. However, we have another possibility like yes, V1, V3 that does not exist. So we have to do additional job to exclude the possibility of an edge connecting V1 and V3. So we need this kind of description. Then maybe the natural question from the audience or our students will be, oh, how about if we just interpret this list not just as a collection or a set of vertices, but some just so continuous flow over our edges. In this case, when you say V1, V2, V3, then we will consider V1, V2, and V2, V3. That sounds reasonable. However, please note that although we are talking about just a two-dimensional structure for simplicity, but your methodology should be easily expanded to the three-dimensional case. Think about three-dimensional structure and two-dimensional terminal which is attached to your three-dimensional region. Then maybe you will have a set of triangles attached to the three-dimensional volume. So in that case, it is very difficult for you to describe your terminal, just a list of vertices. Then you will have a nightmare to build or rebuild the triangles out of the set of just vertices. Okay, Mr. Park, so is it enough for your question? So I just told you that why we have to consider a list of edges instead of a list of vertices. So I hope that it is helpful to solve your question. So, Mr. Park, if you have further question, please feel free to give a question, or if you have understood my explanation, then also leave your message, then I can proceed with today's lecture content. Yes, you're right. So we have to provide the contact file which contains just like you have written uh, in the chatting message. So we have to provide the edge-like list. So we have to our file format should contain the list of edges, not just vertices. So if you have done in a way of just specifying the vertices, then please modify your code. You have plenty of time, so because your code is not written and wasted. Instead, it will be used as the basis for your entire lecture work, so homework. So you have plenty of time to revise your code. So, Mr. Park, if you have interpreted it in that way, then please switch to the edge-like description for your terminals. And also, please allow multiple terminals. So, for example, do not restrict yourselves to just two terminal case or three terminal case. That is not a general way to do that. So in your file, so please try to allow arbitrary number of terminals. Okay. Okay, good. So Mr. Han, thank you for your also feedback. So please convert it to the edge-like description. So that was already covered in our lecture 4. So if you are curious, then please come back to our recorded lecture 4. Then we have already discussed that point. Once again, anyway, it is always good to give me a question. So without the question, so I cannot check your understanding. So otherwise, maybe the lecture will become too difficult because without any feedback, I understand, oh, our students are going really well with my explanation. So then in order to enhance your capability, I will add more and more difficult topics. So if you really don't understand anything, then please interrupt me anytime. Okay, so then why don't we just have some time once again to give you think about further questions. So I will just stop by a few seconds, and if you don't have any further question, then I will move to today's lecture content. Okay. Okay. Then now let's go to today's lecture. So if I remember correctly, now you can specify certain structure, any structure, general structures. So for example, if you did it correctly, even you can make this kind of structure following your homework problem. And also you can specify here certain terminal and another terminal can be attached. Okay, so How about your opinion? Can you do that? So I hope that if you have done homework number 4, the both of problem 1 and 2 are well addressed, then now you can generate such an arbitrary shape quite easily. Looks great. And now you can also identify the interfaces. Okay. Yeah, that is really great. So now you will have region 1 and you have region 2 and you have contact 1 and you have contact 2 and also you have interface 1. So only from certain information like how can I say vertex file and element file, and depending on your implementation, maybe you have some contact file or other file name, or you can just merge it into the element file. So just to attach the, the contents of our contact information to the element file. Anyway, by specifying our structure with 2 or 3 files, 3 text files, you can now generate this kind of information and you can visualize it. So I think that is quite much a big progress compared with at the beginning of our lecture, or even compared with our previous lecture like 2 years ago or 3 years ago, or even compared to our book, the Introduction to Computational Microelectronics. So I think that you are the state of the art in lecture content. So it looks great. Yes, now you can consider any of the regions. So today I wanted to once again give you some time to refine your implementation. So yes, this is contact 1, contact 2, region 1, region 2. However, I'm afraid that actually some of you do it with a limited number, like only 2 regions or 2 contexts. How about your implementation and only one, of course, only one interface? So I wanted to ask to our students about the generality of your implementation. Can you allow 3 or 4 or arbitrary number of regions and contexts in your implementation, or just in order to solve homework number 2, you just introduce a specification like you have 2 terminals and 2 regions. So could you please answer my question? I wanted to check the status of your code. Of course, general implementation is prepared. However, if you just consider 2 regions, right now it's okay, then I will give you some time to generalize it. Mm-hmm. So so okay. Okay, so Mr. Bach, thank you for your feedback. You have implemented in a general way, but have not tested your implementation. So please do so. Mm, okay. So how about other students? Oh, okay. So Mr. Han, so yes. So there are two different contexts here. You are now saying then your vertex file, and yes, later you have multiple regions. So I'm asking that whether so when you just change your vertex positions, that should be an independent job with your region specification. So please separate them. They are completely different job. So exact position, so I mean that double precision numbers like 0, 0, 1, 0 or point 0.5, 0, that exact position of each of your vertex is not that important when we consider really the region specification. So, for example, you can have 1, 2, 3, 4. So, in this case, if we specify in that way, our region file will contain 1, 2, 3 and 1, 3, 4. However, let's say you have just changed the position of your point 1, point 2, point 3 and point 4. In this case, your element or triangle will look like this. However, it doesn't make any difference in your element file. So if your implementation in your implementation, if vertex specification and region specification are interconnected, then please try to make them independent. Of course, region specification really depends on vertex specification. However, once the total number of vertex point is given, after that, everything should be just independent. So, so please try to make a general code. Okay, then our first, our first, how can I say, problem one. So homework number 5. Our problem one is please demonstrate that your code is general enough to consider arbitrary number of regions and arbitrary number of contexts. Are you with me? So, for example, you can think about this kind of structure. Yes, yes, yes. Now, also consider something like this, this, or this. Or if we are getting more closer to our realistic situation, then you may try this kind of structure. Yes, there are 3 different regions and 1, 2, even 3, 4 terminals. That can be possible. So in our problem 1, just to test as many as possible the general structures. So please convince yourself that my code is really working well with multiple regions and multiple contexts as much as the structure is reasonable. Also, please always try to calculate interface. Then natural question is, oh, professor, so we have, for example, in this case, we have a point where three regions are meeting together. In this case, what should I do? So don't worry about that. Interface in this case should be defined as just a collection of edges. So the point is not on edge. So you have to consider region 1, 2, 3. Then you can consider 3 different interfaces which connect region 1 and region 2, and region 2 and region 3, and region 1 and region 3. Then quite naturally you will have interface edges and interface edges and also interface edges, just specifying in this way. Then you don't have to worry about the overall entire regions. So just consider only 2 regions. So interface is solely determined by just connection of one region and the another one. Of course, if we say this is region 1, 2, 3, then if we try to find out the interface between 1 and 2, we will find something. And if we try to find out 2 and 3, then we will find something. However, when we try to find out the interface between region 1 and 3, eventually we will fail. You understand? Then fail means that, oh, region 1 and region 3 has no common interface, so it means that they are really disjoint. They are not connected to each other. So are you all with me? So please try to demonstrate that your code is general enough to consider multiple regions and multiple context structure without any difficulty. So if you did it in a general way, maybe just that will be just specifying or testing your already given implementation. However, if your implementation was not general enough, then please have your time to improve your code. So okay, do you have any question about our homework number problem number 1? So simply speaking, just to have your time to improve your implementation. So please make your code in a general way. That is the problem 1. So any question for problem 1? Any unclear part in your side? Mr. Han, no. So just to consider really a general code. I mean that any vertex file and element file following the rule can be processed by your code. I mean that do not consider any kind of a specific structure. So your structure can be arbitrary. Okay. So, Mr. Park, also when you try to demonstrate your or the test your code, please try to test it with many many devices. So please do not restrict just to one single device or two single two devices. So please make many structures. It can be, so you know that this one in practice this structure will not be used. So but anyway it is good for your demonstration. So you can make such kind of quite a funny structure. Also you can try to implement the realistic structure like a double gate MOSFET or just a single gate, or single gate means the planar MOSFET. Any kind of structure can be made. Also, although I have written down or drawn just in a simplified way, but usually we have many internal structures. For example, this is a side wall. So if we are really become practical, then there will be so many components even inside our structure. So please test many structures. Okay, so simply speaking, Mr. Park, so my answer is do your best to test your code and make really general structures, many structures. Okay, so okay, if you don't have further question on our homework problem 1, then now let's move to our homework problem 2. So simply speaking, our homework problem 2 is now solve the source-free Poisson equation for an arbitrary structure. So I mean that yes, in problem 1 you will make many structures to demonstrate your structure is really working. Then for each structure just to apply certain bias conditions. For example, if you have two terminals, then say just one is biased to 1 and one is biased to 0. Or if you have multiple terminals, then please try to 0, 1, -1 and whatever. So since this system is just a linear system, so the actual value itself is not that much important. So anyway, please solve the Poisson equation. And here I have one caution about that. When you make so it is much better to do that in this way, not a general way. So let me just let me give you the problem a little bit more specific. So let's say that you have n terminals. So let's say that, for example, 4 terminals, then you will have 1, 2, 3, 4. In this case, please do so in this way. Just to apply 1 for your first terminal and set all 0 and solve the source-free Poisson equation, and also solve 0, 1, 0, 0. You understand? Now apply 1 to the third terminal and apply 1 to your last terminal. So you will have n different you will have n cases. Mhm. Finally, you apply just 1, 1, 1, 1. So you will have all 1 for your system, then you will have the solution. Then please try to make a sum of these n solutions. So as a solution of each bias point, you will have the solution 5. So 5 for this condition and 5 for this condition, and yes, for each boundary condition you will have a different 5. Then please make 5 and 5 and 5 and 5. Then draw it and compare it with this 1111 case. So any question about our uh, problem 2? So at least you understand what you have to do. Let's make a concrete example like this. Here we have just a two terminal case. In this case, you apply 1, you apply 1 and 0. Then take the solution and you apply 0 and 1. Take the solution and 1, 1 and take the solution. And after you get these 3 solutions, please try to make a sum of phi 1 and phi 2. Then please make a comparison with your sum of phi 1 and phi 2 with your phi 3. That was my question. If you have 3 terminal device, then please 1, 0, 0 case, call it as phi 1, 0, 1, 0, call it as phi 2, 0, 0, 1, call it as phi 3, and finally 1, 1, 1. That will be called as phi 4. After that, just to make a sum of phi 1, phi 2, and phi 3. Then you will get certain solution and make a comparison with this sum and phi 4. So that is my homework problem 2. Okay, I will explain it a little bit more about real implementation, but first of all, that was description about our problem 2. So if you have any question on homework problem 2, then please let me know. Goal is to solve the source-free Poisson equation. Okay, good, great. Please go ahead. Mm-hmm. Mm, okay, so it will be great to consider obtuse triangles, but for while the main concern of our problem is not the treatment of obtuse angle. Of course, if you can consider obtuse angle, that will be great. But you know, mm, so in my opinion, in this time, so you can just demonstrate that your code works for the structure with triangularized regions with all acute angle, acute triangle, or acute triangle and right triangles. Okay. So anyway, that was a really good question. So think about this one. So first of all, let's just address Mr. Han's uh, question before uh, going into more deeply with the mesh problem. Mm, so I mean that the last example, one next explanation for 100010001 is assigned for our three terminal case. I just gave you a specific example. So please consider this number as just an example and demonstration, and please consider arbitrary number n. So arbitrary number n means that we can have first contact to nth contact, and what you have to do is just 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0. So please label them as phi 1, phi 2, and up to phi n. After that, make a sum of phi I start from n to capital N, and please make a comparison with it with our phi n sub 1, where all large n terminals are biased to 1. So, Mr. Han, is it good to your question? So, have you understood my answer? So, since the structure is general, depending on your structure file, you can have 2 terminal, 3 terminal, 4 terminal, 5 terminal, 100 terminals. Yes, of course, 100 terminal will not be treated in this course explicitly. But anyway, you can assume any arbitrary number for your terminal number. So please check your code with this general number. So of course, when I say general number, then how can we generally prove it? So it's not possible. So please make many structures with different number of terminals, capital N. Then please demonstrate your capability to consider these general cases or many cases. So, Mr. Han, is it enough for your question? Or if you need further explanation, then I can certainly repeat once again. Or please refine your question. When Mr. Han is okay with my answer, then I can come back to the case of obtuse triangles. Okay, good. Then let's come back to the question like this. So think about this triangle and another triangle. Yes. And say this is a right triangle. Then if we try to find out the circumcenter of this lower triangle, then it will be located in this part. Okay, so we have to make lines like this. Of course, we have to make another vertical line starting from this circumcenter to this upper edge. However, the distance is 0 and there is no such line. And how about this one? Maybe we will have also circumcenter over the upper one. So we will have also vertical line. So sorry about my ugly drawing. So I have to be more careful about that. So in order to calculate the circumcenter, we have to find out first the midpoint of each of them. And yes, let's say this is the circumcenter of this upper one, upper triangle. Then we will have yes and yes and yes for a line perpendicular to the edge of our triangles. So when we consider this case, what you can do is treat just lower triangle and upper triangle. Then you will find that in both cases the circumcenter is located internal, either interior or at least the boundary of your triangle. So it is not that difficult for you to make this yellow lines and calculate something. So in that here this yellow line is assigned to this edge and this one is aligned to this edge and this one is aligned to this edge and yes and yes. I hope that everybody in this classroom can now understand, and this width or length of a yellow line, each yellow line is used for the, how can I say, control area of a certain edge. So if we calculate, for example, calculate the flux between this phi of the first node and second node, then we will consider like this: phi 2 minus phi 1 and divide by length between 1 and 2 and length between L 1 and 2 and multiplied by area of 1 and 2. So this length will be area of 1 and 2. Of course, when you say area, it means that actually this is just this is just a length, not an area. However, since we are working with a two-dimensional case, we always assume that there is a certain width hidden in our discussion. we have always a certain unit width which is not explicitly shown in our discussion, but please note that this can be treated as with scale. So that was our current situation. I hope so everybody in this classroom have considered in this way. Then my question is inspired from Mr. Park's question is, now this one is right triangle and this one is acute. No problem. However, what happens if we further push our lower triangle? So this node, oh sorry about that, if we push this node in that direction, then what will happen? That is my concern. So let me just do it together with you. So if we have a right triangle, let's say this is right angle, then our new triangle now given as this way. Let's assume in this way. Certainly this one is obtuse. So, and think about another triangle. Yes. So certainly it is acute. Then first let me try to find out the circumcenter of this guy. Yes, let's say this is the circumcenter of your first triangle. So are you all with me? Then let me just calculate the obtuse triangles So where can you find it? I think that I should be a little bit more careful about find out midpoint. Okay. But I think that let's say this is anyhow right angle and right angle. Yeah. Then now we have a circumcenter is located outside of our original obtuse triangle. So then please think about this one. So for the acute triangle, now you will draw in this way without bordered by any consideration of neighboring triangle. You will get it. So problem is the length for this edge. Okay, now you can understand according to our acute triangle, then this one this will be the area corresponding to our edge shared by our obtuse angle and acute angle. So you know it. However, in reality, what is the division of our shape? In this case, our control volumes are divided into this way. And finally, we have this part. So, if we draw the magnified view of our case, so let me just draw here. Then we can think about this case. This is the circumcenter for acute one. Then usually we will have this line, and yes, there will be certain edge corresponding to, here we have a certain edge corresponding to this area. But important thing is, if we have an acute triangle and if this angle is obtuse, sorry about, not acute, obtuse. So if this angle is obtuse, then it is certain that our circumcenter will located somewhere here. Okay, here we have a circumcenter of our obtuse triangle. Then for this edge, so black colored edge, we have to consider only this length as a meaningful area for this edge. If we consider this guy, then we are now overestimating the area for our edge, so the black edge. So, Mr. Park, so can you understand my explanation? So if we have an obtuse triangle, it has its own circumcenter outside its boundary. So every time when you have an obtuse angle, this obtuse angle just to invade another or neighboring triangle, and with the invasion of this obtuse triangle, we have to carefully change the area, controlling area assigned to each edge. So that introduces really a problem when we consider the obtuse triangles. So, Mr. Park, are you with me? Or this is not just not specified to Mr. Park. So every student, our three students, should understand this issue. So when we have obtuse triangle, then the previous consideration, consider only the circumcenter locally and calculate the length or width corresponding to perpendicular to each edge, that does not work for this case. So that makes our problem more complicated. So that's the reason why for a while I just recommend you to avoid this issue. So of course you are willing to try to solve it. That is great. So that is really encouraged. However, I think that right now, please concentrate on just the treatment of a general structure. That is more important right now. So once you can treat the general structure, then after that you may spend your development time on the treatment of more general mesh component with obtuse triangles. So, Mr. Park, are you okay with my explanation? Or how about our all three students? So you must at least understand this issue. So obtuse triangle, its circumcenter is located outside the triangle, so that complicates for calculation of a control area. Okay. So now, now I think that I think that it is better to cancel our problem 2 right now. So because in order to actually solve problem 2, you need more information. So that will be explained from now on. So I will just postpone the post of problem 2 explained up to now to the next session. So please consider only the homework problem number 1. It means that please test your code with many general examples. So create your example and test your code. Yes. So now you please understand, now you have only one problem in this homework number 5. Why I'm asking you to solve just one problem is when you try to solve the source-free Poisson equation, then now you have to consider the problem of interface. And this problem of interface is really closely related with how can you assign unknown variables. So since this is not a simple issue, so that's the reason why I just postpone giving you the problem 2. Okay, so please repeat that. You understand you have only one problem. Okay, so please leave your message that your second problem is cancelled and postponed, and now you can solve just one problem, demonstration of your code. Okay, good. So how about Mr. Park? Okay, then maybe you are a little bit curious why he just cancel already explained hormone number 2, but that is really related with setting unknown variables. So let's go to more, how can I say, simplified example. So let me just simplify it. I wanted to introduce certain discretization of this really pretty structure. Now we have think about only oh. Now let's assume that our really pretty structure is now discretized with really small number of points. Oh, maybe you feel that that is too crude. Yes, that is too crude, but I intentionally make it too crude to show you that this is an issue not related with the fineness of our description. So let's say that now we introduce many triangles. Hmm. Hmm. Yes. Yes. Now you understand. Although that looks really ugly in some sense, but anyway, it describes the overall shape of your structure. Yes, and yes, yes. Now you have it. If you have such kind of thing, how many points are there? One, oh, say just this one is a one. This one is, you have a one, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes, now we have just 13 point, and yes, we have anyhow two regions and two contexts and one interface. So when you process it quite well, then you will find that your interface will have some information like that. For example, 4, 8 edge is at your interface, and 8, 6 is also in your interface, and 6, 7 will be at your interface. Yes, you have 1, 2, 3, 4 vertex nodes, and they are belonging to the interface. Then now you wanted to assign your unknown variables to your 13 points. You have a 13 points, so your obvious choice is I will assign phi 1, phi 2, blah blah blah, up to phi 13. That is your usual choice. I mean that 4, 5, 4. What is meaning of 5, 4? We have a vertex 4, and that is 5, 4 is our solution variable assigned to vertex 4. What is 5, 6? Yes, now we have a vertex 6, and that is the solution sampled at vertex 6. So you understand this concept quite easily. But sometimes this kind of concept is not supported. Mm, I'm just showing you certain counterexample. Think about this simple case. Now you have silicon. Now you have oxide. And you have a certain point here. And instead of phi, which does not have any physical meaning up to now, think about electron density or hole density, any kind of carrier density. Then I'm asking you, what is electron density at this point? Then maybe you can answer me like, oh, professor, there is 10 to the 20 per cubic centimeter electrons there. Are you sure? Are you sure about that? Then let me just magnify this part. Then we will have, yes, we will have a certain point here, and this is oxide, and this is silicon. We know that we have plenty of electrons in this case. Then my natural question is, how many electrons? In this point? Or if we approach from this point to that point, what is the change of electrons? You know it. There will be no electron. And when we consider silicon, of course, there will be plenty of electron. I mean that even for a single vertex, depending on material property, same physical quantity can have different values. That is my concern. So we will continue this discussion in next Monday. So please note that we have one single homework problem, and I wanted to give you sufficient time to refine and improve your own code, because your code is really precious to you, because with that code you will solve all of homework problems, and even for a final presentation in this semester. So that is quite important. So please have your time to make really general code. Okay, so time is up, and if you have any further question, then please contact me through Slack or email or whatever. So see you next Monday. Bye.